Hey everyone, Chris here. For this differential equations project, I looked at Newton's law of cooling, but with a pretty realistic setup. Usually Newton's law assumes the surrounding temperature stays constant, but in a small enclosed space, the surrounding air can heat up too. So I modeled two changing temperatures instead of one. I used a turned off microwave as a small enclosed chamber because I didn't have anything else very well insulated with me, and then I never turned it on. I put a container of really hot water inside. I closed the door and measured two temperatures over time, the water temperature and the microwave air temperature. And then I took data every 2 minutes for 30 minutes. The goal was to build a differential equation model, predict what should happen, and then compare it to the real data that I collected. So here I let AT here, lowercase at, be the temperature of the water, and then capital AT be the temperature of the air in the microwave. So the key physical principle is that heat transfer is driven by the temperature difference. If the water is much hotter than the air, then the heat flows faster. So if they get closer in temperature, heat flow slows down. So I used a simple proportional to the difference model here as I model here. So here's what these mean in plain terms. A minus capital A is how much hotter the water is in the air. The water should cool, so dA over dt should be negative when A is greater than capital A, which is water greater than the air. And then the air should warm at first, so dA dt should be positive when A is greater than capital A, which is when water is greater than air. So here, depending on how you define the constants, the signs work out. The important idea is one equation makes water move toward air temperature, and the other makes air move toward water temperature. It's a two-way heat exchange model. So instead of solving both equations directly, I focused on the temperature gap here as I modeled with this equation between the air and the water. So this is how far apart they are, the function. So this is how far apart they are function, I'd say. Here I differentiated both sides, and then I substituted in the model equations here. So it would leave me with this equation. But notice that the air minus the water here with this factor is the key simplification. So as I modeled here. And since dt equals water minus air, we get this equation. And that's great because this is now a single first order differential equation. So what does that equation predict is the big question. Well, the equation has the standard exponential solution, which is a very big deal, meaning the temperature difference should shrink exponentially over time, assuming K1 plus K2 is less than 0, which corresponds to the system settling towards equilibrium. So the model predicts the water and the air temperatures get closer and closer, and the gap shrinks fastest at the beginning, and then it slows down. So how did I test the exponential prediction? Well, to test exponential behavior, I used the classic trick of just taking the natural log, starting from this equation here, and then I took it on both sides. And so if the model fits well, a plot of ln of water minus air, the A minus A, versus time should look roughly like a straight line, and the slope gives an estimate of K1 plus K2. So here I have the first graph with the function of water and air modeled. In my data, the water temperature decreased over time. The microwave air temperature increased during the first 10 minutes, which supports the idea that heat was transferred from the water into the air. The difference of water minus air dropped overall, meaning the two temperatures moved towards each other, exactly what the model expects. When I graphed the ln of water minus air, the first 10 minutes looked the most linear. That's when the microwave air is clearly warming and the two compartment model is most accurate. After that, the air starts dropping, meaning heat is also leaking out of the room of the microwave. So the takeaway here is that a simple system of differential equations can model heat exchange between water and trapped air, and the math predicts an exponential decay. of the temperature difference. So the experiment does support that, especially in the early phase. Later on, the microwave isn't perfectly insulated, so a more detailed model would include heat loss to the room, and in the future, maybe model with a more insulated type of compartment. But yeah, overall, that's how it went. So thank you everybody for watching, and bye bye.